correlation is usually reported through these things called correlation coefficients, and these answer basically our desire to measure a linear relation. So what we want to know is, well, is there a linear relationship? If there is, how strong is it, right? So some relationships are more clearly seen and more clearly revealed than others. So we want to know how strong the relationship is. And this is usually done through some kind of a measurement called the correlation coefficient. Usually the correlation coefficient that people use is Pearson's R that we have seen in the fall. You may want to review a little bit your notes and the classes on that one. And occasionally when some of the requirements that are behind the Pearson's R measurement are not satisfied, especially in the analysis stage, we use an alternative one called Spearman's rho. Usually Spearman's rho comes from situations where our data are in fact ordinal or have some other kind of strange feature that makes the use of Pearson's R a little bit uncertain. A quick reminder of what we saw in the fall about these correlation coefficients. First of all, remember these coefficients are built up in such a way that their value is always between -1 and 1. Okay, so even though they look close to probabilities, but they can be negative, so they can go either way. In fact, a correlation coefficient near -1 means that we're looking at an inverse linear relation. That means as the x variable goes up, the y variable goes down, and that's demonstrated through this downward pattern of these dots. Okay. On the other hand, a correlation coefficient near +1 means that there is a direct linear relation. Okay. Now, the correlation coefficient does not tell you anything about the slope of that relationship. So again, that's something that would have to be looked at through regression, not correlation. But it tells you how tight those dots are and how good of a linear relationship there is. Okay. So if we have a correlation coefficient near 0, it means that there is no relation, like in this case. Now you might wonder, well, I do see somewhat of a downward pattern here, okay? But there are a couple of things to be noticed. For one thing, perhaps this pattern is highlighted by this particular observation, okay, which pushes the pattern, which makes it look like it's going down. And this brings up again the issue of the fact that in correlation as well as in regression, individual outliers can have a strong impact on the value of the correlation coefficient. On the other hand, even though we may consider that individual outlier, the pattern is really not very strong anyway. Okay, so we may not want to think too much about this relationship. But there is a bigger point here, and that is that the absence of a linear relationship can exist even when there is a relationship. For instance, in a situation like this, the correlation coefficient is probably going to be very close to 0, because remember, the correlation coefficient measures linear relationship, and in this situation what we have actually is a curved pattern, right? So this pattern is going up and then it's going down again. And so in that situation what we're going to have is also a correlation coefficient which is going to be practically 0, indicating the absence of a linear relationship. But that's not a good enough reason to abandon any search into the relationship between these two variables, as we're going to see again in a few minutes. So always keep in mind that with these correlation coefficients, what we're looking for is a linear relationship, not just any relationship. And by the way, this is one of the most important problems that occur in correlation regression analysis, the fact that people forget to check what kind of relationship there is, and they jump into linear correlation analysis, even when in fact they should be using a different kind of analysis. So in order to really find out if we're in the presence of a linear relationship or not, probably the easiest way to check is to use a scatter plot. And that's why you may remember that even in the fall I mentioned that scatter plots are a really essential tool in bivariate analysis. When we're trying to relate two variables, we need to do, and if those two variables are numerical, we definitely need to have a look at the scatter plot. The scatter plot can tell us way more than just a correlation correlation coefficient or even a regression line. Okay, so the few things to remember here is that the value of R by itself may be misleading, be it R or Spearman's rho, doesn't matter. Still, by itself it can be misleading. It can tell us things that are not really, can lead us to conclusions which are not correct. Okay, in particular, the reason for that is because a curved pattern may alter it. We're going to look also, when we look at regression, at some other things that may influence mostly the regression part, but certainly the curving of the pattern is something that affects at least the correlation coefficient. On the other hand, once again, remember, nonlinear patterns can be useful, can be interesting, can reveal some information that could be very, very important. Okay, so just because a pattern is not linear does not mean that we should ignore it. In fact, sometimes they are the more interesting patterns. The point is that we cannot address them by using regular correlation analysis. They must be analyzed differently. So always demand that a scatter plot be included, or at least that the authors tell us that yes, they have looked at the scatter plot and the scatter plot does reveal a linear pattern before we can accept anything else they say about the correlation coefficient.